Okay, folks, we're taking a look at 13-2 notes on neutralization reactions as part of our acid and base unit. By the end of this little short video, we should be able to predict the products for a neutralization reaction and write the net ionic equation involving acid and base reactions. These are concepts that we've covered in our last unit, so hopefully a lot of today will be a review. A double replacement reaction occurs between two ionic solutes that have been dissolved in water, meaning that they will dissolve and dissociate. That's why they get the aqueous designation. An ionic solute always is comprised of two parts, a cation and an anion. And when these are dissolved in water, the positive and negative poles of the water will attract and separate the cations and anions from their current partners, and as all the particles are moving, the cations and anions will find new partners. So we're going to put the outside ions together, making a new compound AD, putting cation before anion, and the inside ions will find each other and we'll put them together, cation before anion. Now, since this is occurring in water, if one of these products is a solid, a liquid, or a gas, we'll know that the reaction occurs. If both products are aqueous, then we will not see a product and the reaction does not occur. So we will know if a compound is a solid because we're going to check our solubility table. Liquids, there's only one liquid that you need to look out for, and I think you recognize it as a liquid, which is H2O or HOH. There's two gases that you should recognize. I think we know CO2, and the other one is H2S. A neutralization reaction is a double replacement, except that it occurs between an acid and a base. I recognize this template as an acid because there's a hydrogen ion in front. This X is representing the charge on the anion. I recognize this to be a base because of the hydroxide in the back, and I recognize this subscript of Z to be the charge of the cation when I uncrisscross and split. So when I put the outside ions together, the charge on hydrogen is +1, the charge on hydroxide is -1. So when I put these two together, the cation first, I'm always going to get HOH, which I recognize to be liquid water. And then when I put my cations and my anions together, when I uncrisscross and split, my anion is going to have a negative charge of X, and my cation is going to have a charge of positive Z. So when I put those two together, the cation goes first, the anion goes second, and when I cross and smush plus Z minus X, I'm going to get XZ as my subscripts. And then more times than not, this will be aqueous, but we'll want to double check our solubility table just to be sure. So our two products will always be water and a neutral salt. Now, salt is a very general term in science. It just means that it is not carbon-based, nor does it have hydrogen or hydroxide in it. So if we were to draw a model, I'm going to draw acid on the left, and I'm going to draw base on the right. For this model, you've seen me draw a lot of acid as H3O+. But for this reaction, I'm just going to show the H+. And we also know that acids are going to have more hydroxide in them than I'm showing. So right now I'm only showing you the ions that are switching and taking the place of each other. My cation is going to get in here, my anion, is going to go in here too. And then my base, again, we know that there's hydronium in a base solution. I'm not going to model all of that. I'm just going to model what's in my, just modeling the moving parts. So here's my cation with a +Z charge, cation with a +Z charge, cation with a +Z charge. Okay, So when I put all these guys together, my HOH is going to find each other. And my cations and anions are going to find each other. Now, since they are aqueous and they're going to dissolve and dissociate, they're going to be separate from one another. They're just going to be separated. So you notice that the water, the HOH, is staying together. It does not break apart. So when we write our net ionic equation, our neutral salt will dissolve and dissociate, but the water we keep together. There's our not a terrible model. Okay. So now our speed dating neutralization reactions. I'm just going to choose a couple. We won't speed date today, but let's say we're going to draw we're going to write the equation between ammonium hydroxide and hydroiodic acid. Okay. So I'm going to put my outside ions together, which I recognize as being ammonium and iodide. So we have an exception, one of our ninja ions. Here's our polyatomic ammonium. And here's our cation, our monatomic cation. So we're going to put outside ions together. Ammonium has a charge of +1. Iodine has a charge of -1. So when I cross and smush, their subscripts are 1 and 1. And then I see H and OH. Hydrogen has a charge of +1. Hydroxide has a charge of -1. So I'm just going to write HOH. You could switch it back to H2O if you want. When I look at my solubility chart, ammonium or iodide is soluble with most cations, and ammonium is not one of the 3 that are listed as a precipitate. So I'm going to call that an aqueous. And then HOH I recognize as water. Now for the net ionic equation, remember we have to we dissociate everything. So I'm going to just write our complete ionic equation first. So there's our ammonium, our hydroxide, our hydrogen, and our iodide. So anything that's aqueous, we're going to dissolve and dissociate. Each one of these is aqueous also. Our ammonium iodide is also aqueous. So I'm going to dissolve and dissociate that. But the water, this is not aqueous. It does not dissolve and dissociate, so we're going to keep it together as HOH. We're going to keep it together as a liquid. So our net ionic equation is after I've taken the spectators out, I see that I have an ammonium ion and another ammonium ion on both sides of the arrows that remain unchanged. And I have an iodide ion that is aqueous on both sides of the arrow. So those are my 2 spectators. So for a neutralization reaction, my net equation will always be hydrogen ions in solution plus hydroxide ions in solution will always produce water or H2O. Okay, now we do one, now you do one. Why don't you try lithium hydroxide and phosphoric acid, H3PO4. Again, these are both aqueous. Why don't you give those a shot? Okay. And for the last one, we'll do one more together. We're going to do barium hydroxide and acetic acid. Both are aqueous. Okay, so we're going to split these up. Barium is a +2 charge. Hydroxide is a -2 charge. Hydrogen is a +1. And acetate is one of our ninja ions. It has a -1. So I'm going to put my outside ions together. There's my neutral salt. I get barium with a +2, and acetate is my anion. It goes second with a -1. So +2 -1, when I cross and smush, 2, 1 becomes 1 and 2. And then my hydrogen is a +1 and hydroxide is a -1. We're going to put our cation before anion, and again, there's our water. So there's my liquid. When I look up acetate, barium is not on that list, so we're going to say that's aqueous. And for my net, I'm going to write my complete ionic equation first, which just means that I'm splitting up this aqueous compound, this neutral salt. Here's my neutral salt. I'm going to split that apart. And I notice that on both sides of the arrow, my barium ion is still in solution, and my acetate ion is still in solution. So again, my net ionic equation is hydroxide ions in solution plus hydrogen ions in solution. And that gives HOH. All right, so go ahead and try number 2, and we'll go over that one together in class. Thanks.